You have all probably heard of marine heat waves recently, a phenomenon that kind of became well known after the so-called blob that appears here off of Canada and US in the northeastern Pacific and has had serious ecological consequences. And of course, we know that there are tropical corals that get bleached even on El Nino time scale. So the question is whether the warming in the ocean that occurs rapidly are the heat waves increasing in the ocean. If you look at the sea surface temperature, I think there is a breeze that's going to affect the sound, so I'm going to close the window first. Okay, so obviously marine heat waves then have to be looked at carefully. If we looked at the sea surface temperatures like we did before, then obviously tropics have warm temperatures, upwelling regions have colder temperatures, latitudinally the temperatures cool off. So when you say heat waves, you have to think about the background sea surface temperatures and their seasonal change. Because the ecologies, whether it's corals or fish or something else that you're worried about, have evolved, let's say, over time to live in a particular environment, maximum temperature, variability of temperature, and how they are affected by heat waves will depend on how the heat waves are defined. So there have been metrics used like we did for extreme rainfall, saying anything above the 90th percentile at any time of the year can be defined as a heat wave. But during the cold times, if temperatures rise above the 90th percentile, it may not matter. So this paper I'm going to go through is basically arguing that it's the warm season exceedances of temperatures that are critical. So the heat waves, marine heat waves, should be defined with respect to this. It's not by any means a agreed upon or a consensus view, but it doesn't matter in terms of just presenting the concept here in this introductory course. Keeping that in mind, this is a good example of a marine heat wave. This is from September 2014 and this is from September 2019. So this was kind of a warm tropical Pacific during that time, which didn't quite qualify as an El Nino, but 2015-16 was a monster El Nino, the biggest one of this century, of course, and comparable to 97, 98, 82, 83, 1997, 98, 1982, 83 as well. So in the tropics you can clearly see the tropical instability waves as well, but this California current warm blob had serious consequences. So understanding whale entanglements in the US west coast. This is an infographic from NOAA Fisheries. So this is the summary of oceanographic and ecosystem changes within the California current during marine heat waves. The synthesis of information on changes in ocean and forage species described in this study provides the basis for establishing an ecosystem oceanographic perspective and so on. So here you have the California coast. Let's read a few things. This is the continental shelf out to 200 meter depth. 400% increase of confirmed whale entanglements. Fishing gear are shown here. So is there a relation? So you have crabs and anchovies and changes in Dungeness crab fisheries. Harmful algal blooms delayed the opening of the fishery in 2016 following the strong El Nino. More crab gear when whale concentrations were high. So the natural event like El Nino is affecting the fish, and the fisheries management is deciding when to allow fisheries, and the whales are responding to availability of food as well. So you have these multiple confluence of events. Changes in ocean conditions, persistent marine heat wave, massive bloom of toxic algae. changes in whale's prey, lower krill abundance off shelf break, switch to low abundance anchovies near shore. So krill was gone because of the heat wave. Let's say anchovies are there, so the whales go to eat whatever they can get. Humpback whales seek other prey further north, so there is also a change in their feeding grounds. Changes in whale presence and abundance, recovering whale populations. Humpback whales switched prey found closer to the shore. So fisheries management didn't necessarily include all these things in their decision, neither did the fishermen. So management and mitigation. Fishery management coastwide could ask these following questions related to entanglement before and during seasons and take actions as a result. Are there delays in the fishing seasons or other factors that may lead to higher fishing effort when whales are on the fishing grounds? Does the distribution of krill and forage fish on fishing grounds suggest an increased risk of fisheries interactions with the whales? Are there known or expected high concentrations of whales on the fishing grounds? Are there recent higher numbers of whale entanglements in the fisheries or nearby? So you can see how complex it gets. So heat waves can then be defined based on such ecological impacts, or they can be based on thresholds within the temperatures themselves, and then whether it could be the 90th percentile exceedance, or something like monthly mean, maximum monthly mean temperature and temperatures above that, and so on and so forth. So the definition from this paper that goes into the NOAA's Coral Advisory says, hotspot, a measure of daily coral heat stress and degree heating week, a measure of accumulated coral heat stress are defined based on maximum monthly temperatures. Hotspot is a positive anomaly product based on the difference between daily sea surface temperature and the maximum monthly mean MMM. Climatology, so long-term climatology, so you assume that there is some ecological evolution to deal with the maximum monthly mean in a year on the long time scale, and any exceedance above that is going to have a consequence. And then you have to think about frequency, duration, and intensity. Unlike the rainfall, the difference is that the ecological systems also worry about accumulation of heat. So typically we worry about extreme events, but not necessarily accumulation of rainfall over time and so on when we do extreme rainfall events. Whereas degree heating week is an accumulation of hotspot values. Okay, keeping that in mind, I'm going to go into this paper in a little bit more detail. Lengthening of warm periods increased the intensity of warm season marine heat waves over the past 4 decades. So they are taking a period of 1985 to 2019, which has a warm ocean signal in it, and of course natural variability like PDO, Pacific Decadal Oscillation, North Atlantic Oscillation, as well as Southern Ocean modes, and El Nino, of course, La Nina, etc. And because the warm period is used to define maximum monthly mean values, the thresholds are already probably above, let's say, compared to the periods before. And you leave the question open about whether the corals and other ecological systems are affected by the warming, or they have adjusted so that we can define heat waves with respect to this warmer period and so on. But leaving those kinds of details aside, here is a table of the metrics measuring the warm season marine heat wave characteristics. Hotspot, as we said, based on maximum monthly means or 90th percentile, and they also define a peak hotspot value. The durations are basically defined as continuous positive HS values, total number of days with positive HS values. DWS is a warm season, basically hotspot warm season length, which we will see graphically in a minute. And DP is number of days between the first positive hotspot and onset of a continuous positive hotspot. This is called conditioning or priming period, which is based on the assumption that a sub-lethal heat wave will prime the system like a coral to get ready for what may be coming. It's like saying when the summer is going to arrive, the first warm day may allow us to bring out our summer clothes, let's say. Okay, very vague metaphor, but there it is. Then the accumulated heat stress days are also important. I hope the idea of degree heating days and degree cooling days, in this case duration of hotspot days and so on, is obvious. It's easier to explain in terms of what is done in the energy industry. For example, they have a concept of cooling degree days, which means, let's say everybody prefers a temperature of 25 degrees centigrade or something like 70 degrees Fahrenheit. Then anytime the day is warmer than that threshold, let's say you want to set the temperature at 25 degrees as comfort level where AC will kick in if temperatures are above that, then a 30 degree day will give you 5 cooling degree days. So if in a month you have 6 such days of 5 degrees above, then you will have 6 times 5, 30 cooling degree days in a month. So this is kind of approximately how you think about these. In the ocean, of course, the difference is the ecological systems also care about accumulation of heat. So accumulated heat stress in degree C days is defined. AC is the accumulated sum of heat stress during the continuous positive HS days based on the time period used for DC. We'll see the graph again in a minute. A total is the accumulated sum of all hotspots that year. Okay, DHD is the degree heating day, which is a derivation from the degree heating week that the NOAA Coral Advisory uses. Similar concept. So maximum 84 day, that is 3 months continuous accumulated sum of positive HS in a year. Basically they're only using warm period of the year, warm season of the year. So within 3 months of that season, how many accumulated HS days you get. Okay, mean heat stress intensity is the average hotspot value over the continuous positive HS period. So it's basically AC divided by DC. Heating rate is done for a rate of SST increase from the first hotspot in a year to the date of HS peak. HRC is the rate of increase from start of the continuous HS day to the HS peak day. And there are heat stress levels, level 1, 2, 3, 4, similar to NOAA's advisories, which go in this paper as degree heating day greater than 0 degree C day, which NOAA doesn't use usually. Degree heating day greater than 28 degree C days, so this is converted into something like 4 degree heating week according to NOAA's metric, and degree heating day 56 degree C days, and degree heating day greater than 84 degree C heating days. So remember, these are not temperatures, these are the differences from the threshold that are converted to degree heating days. Okay, so here is the way to look at it graphically. This is the seasonal cycle at any given location. So you're coming out of the winter towards the warm season, so there is the maximum monthly mean temperature, which is one value for the year, and then you have a threshold above which, when you first cross, you get DP, which is the priming day, okay, as we said before, and then the continuous HS days occur here up to the HS peak, and then there is a decay, and then there is a seasonal cooling. So you have dp is the priming period here from the first exceedance to the continuous d, and there is the HRC, continuous heating rate, and this is the heating rate from dp to the peak. This is the days of the warming season going from the first exceedance to the end of the last exceedance. Okay, so just keep those in mind, and the main message is fairly simple, that it is the trend in the duration of the exceedance days or HS days that is causing the increase in that is the biggest reason for the increase in the duration, intensity, and peak of the marine heat waves, and there is a combination of natural modes as well. So let's look at a few results here. This is the trend in warm season marine heat wave characteristics from 1985 to 2018. Sorry, I said 2019 before, that's wrong. Here is the duration of the continuous warm season, so DC, and you can see that except for the far eastern tropical Pacific, there has been increases in DC, the continuous, so this has increased in trend over this period, and the scale is here in terms of days per year, and obviously there is some relation to the warming rates. So the ITCZ here and the Western Pacific warm pool region shows the largest increases in DC. All the stipple regions are statistically significant, and it is argued in the paper that these particular trend lines as negative to positive at 50 south or so and 40 north or so are related to the conflation of things like the Pacific Decadal Oscillation, North Atlantic Oscillation, and so on into these calculations. Okay, B is basically the number of annual total HS, so D total days per year. So now you can see that there is a negative number here, so the continuous HS days have increased, but the total numbers in a year have decreased as a trend. And even more interestingly here, C is the number of days between the onset and the end of HS in a year, i.e. the warm season length DWS that we talked about. So you can see that the trend is very mixed here, and it's a large negative trend here, whereas the Western Pacific warm pool retains trends in this as well. So this basically tells you, especially when you look at this in terms of heating rates, so D is the number of days between the first HS of a year and the start of a continuous event with annual peak HS. So this is the priming period dP in days per year. So you can see that that has decreased, which is consistent with the fact that overall the duration of the heat waves have increased. So there is no gap between the first exceedance to the first arrival of a continuous HS number of days. Okay, so the heat waves are just kicking off and they are immediately increasing in duration. There is nothing like a signal for priming the system, corals and other ecosystems, so they are getting hit because the warm season starts immediately. There are long duration marine heat waves according to this MMM threshold, where we are using maximum monthly mean values as the threshold. Okay, I hope it's clear. So it's not the increase in intensity that's causing these, and it's not the increase in dP that is causing it. It's the increase in DC, the total duration of continuous HS days, that is causing the trends in accumulated heat stress. Okay, so looking further details, trend in warm season marine heat wave characteristics from 1985 to 2018 in terms of the accumulation of heat stress of the continuous warm season MHW. So this is the AC in degree C day per year, and B is the so here you can see again mostly all positive but more patchy than this figure, for example, which is the trend in DC. Okay, so B is the accumulation of annual total HS, so it's A total degree C day per year. Remembering that accumulated stress is important, we have to add some physics to explaining why the heating rates are decreasing at the same time that duration and accumulated heat are changing or increasing. Okay, so C is the heating rate from the onset of a continuous event to the annual peak, so that's the HRC. So that is this here. So you look at this and this. If this is increasing and this is decreasing and this is decreasing, this is also decreasing, that means the accumulated heat is not increasing because of the increase in the peak HS, neither is it increasing because of the heating rate increases either in the continuous period or in the seasonal period. Okay, what does that mean? That means there may be some kind of a thermostat effect that is probably in play. So C here is the heating rate that we talked about, HRC, and this is D is the heating rate from the first HS of a year to the annual, so that is HR. Both have largely negative trends except at these bands here, which again is a conflation of PDO and NAO and so on, which are natural variabilities which can add to the computation of these thresholds here. So that means that you can increase the duration of continuous HS days and the peak, whatever the other D total HS days, but without increasing the heating rate, which means warming happens, but there is a thermostat effect which is discussed separately in various papers like Amy Clement's paper and Luo's paper and so on, which basically says that when you try to warm the ocean, especially the Pacific Ocean, whether the warming will continue to accelerate or not will depend on how the East Pacific responds. So if with the warming East Pacific warms less than the West Pacific, then the sea surface temperature gradient will get stronger, winds will get stronger, which means upwelling will get stronger, so the ocean's ability to take up heat will get stronger, which means the warming will be modulated. But in the case of marine heat waves, that is also related to the coupled processes of the Walker cell and the ocean heat uptake itself. So more ocean heat uptake here doesn't necessarily directly affect the trends in the Western Pacific warm pool. It is going to act through the coupled air-sea interactions and the Walker cell and so on and so forth. Okay, so sounds complicated, but just remember that this basically says that marine heat wave continuous days and total days can increase without the heating rate increase or peak intensity increase. So E here is the annual peak HS in degree C per year, and that also shows negative trends here with the Western Pacific warm pool region maintaining some trend plus maybe something here, but this is quite patchy, and you can see there are no stipples here, which means it's not statistically significant either. Okay, so complicated sounding story, but basically remember that intensity, duration, and accumulated heat in the ocean, marine heat waves in the warm season are increasing. The increase is largely related to the increase in the duration of hotspot days, and not the increase in maximum intensity of the hotspots nor the heating rates, and that's where the ocean dynamics in regulating ocean warming may be involved as well. And the spatial pattern also tells us that natural modes of variability may be involved as well. So this is finally the change in frequency of the years with warm season marine heat waves at level 1 or above, so degree heating days greater than 0. So anytime you have one exceedance, you immediately cross the 0 value of degree heating days, and you can see that large regions have positive trends in frequency percentages, but there are of course these patterns which have negative, again maybe related to the thermostat effect or the natural modes as well. In B, we are looking at level 2 or above, so greater than 28 degrees C days, or what NOAA would call degree heating week of 4. I think again there is a massive increase here in the West Pacific warm pool, and maybe the PDO impact here, and advection of heat by the East Australian current, maybe by the Gulf Stream, and so on. So changes in dynamics and wind circulation may be confounded in this as well. And C is the degree heating days greater than 56 degree C days, and this is the finally greater than 84 degrees C day, or the basically a season. So this is like the D total. Okay, so you can see that here there is a negative trend here, frequency decrease here in all of these measures, but West Pacific warm pool stands out in all of them, but not so strongly here at the seasonal total. Of course, you have to remember the mean temperature in the Indian Ocean is always high, so the ecosystems within that are still have still evolved to take the maximum monthly mean temperature of the year, and then responding to the marine heat waves. In other words, these are physically based indicators which show how anthropogenic warming is affecting marine heat waves. Then we have to probably rely on ecological metrics to see which ones are significantly affecting ecosystems in terms of accumulated heat stress, and whether it's the duration or accumulated heat stress that are critical for ecological damage. Okay, let me leave it there. It's a bit long, but that's okay.